See a tree, right? Remember, we always say that a picture is worth more than 1,000 words. So I thought of finding why. I know you are used to this, okay? You know this very well. And you can actually see that tree has some prominent features, right? You have the root, you have the stem, then or your main branch, and then you have your branch, and then you have the leaf, right? Right? So there you got the leaf. So you can as well see the leaf here, right? And so this was another branch. So we'll be looking into decision trees, right? So in machine learning and even in data mining, and generally even in your basic artificial intelligence class, you must have learned about using decision tree to make some salient decisions, right? So in life, we make decisions almost every now and then. Decisions about where to go, what kind of clothes to put on, what should I have for breakfast or lunch or dinner, whether I should accept a job offer or not. You know, there are lots of decisions we make, right? So looking at this, why can't we somehow model this so that by using some algorithms we'll be able to understand how actually decision tree works? So you see, as a representation here, you can see the root, right? And then you see your stem, goes to branch, and the leaf. So is it that this is what you are going to do in decision tree? Something similar to that. Okay? So this really mirrors whatever you've seen there. So how can we define a decision tree before we look into the algorithms? Yes. So a decision tree is a tree in which each node represents a feature or an attribute, and each link or branch represents a decision rule, and each leaf represents an outcome. So let's make a small decision tree whether to accept a job offer or not. Please remember, I will superimpose this, okay? Leaving this tree here, maybe it will be cluttered. Why don't I erase this now? Now we've seen this, right? So keep that in mind. What are we going to see now? We're going to see nodes, right? Attributes, and what? Leaves, right? So the node, you call it as your root node. So usually we say here, this is the root node. Okay? So this represents your what? Your decision rule. Decision rule. And this represents your what? Say outcome. Now, I'm going to superimpose something on this, okay? So let's say we want to make a decision tree whether to accept a job offer or not. A simple decision tree, which everyone can make. So what will be your primary root node? Can anybody tell me? What should be your primary root node? See, most of us will look at the salary first. Before any other constraints, we check the salary. So you have decided that the salary is what you're going to consider. So salary is your root node, right? Fine. If salary is your root node, what are you going to consider next? Now, how much is the salary, right? So I'm going to expand this now. Instead of just writing salary alone, I will make it this way. So this is salary, and it has a constraint. Is this salary greater than 4 lakhs per annum? For most of you, even freshers also, they want 4 lakhs per annum salary. Anyway, so if it is greater, oh my goodness, I will not even consider anything. Maybe I will accept the offer. Now, so the company tells you, see, because of the pandemic, we are running into financial crunch, so it is not greater, right? So is this greater than 4 lakhs per annum? No. Immediately, what the student does is reject offer. Reject. So this is my leaf node, right? So this is my leaf. So this is a pure outcome, right? So I'm already done with this. It's not greater than 4 lakhs per annum. Why should I accept the offer? I rejected it, so I've reached my leaf, okay? Or my pure outcome. Now, if it is greater, again, you say, okay, fine, let me go think about it. Because my mom may not want me to leave Mysore. She wants me to stay in Mysore only. Now, if it's greater, Now I will check what again? Maybe I check work location, right? So work location, maybe I translate it into the average time it takes to reach to my place of work. So I might check work location. Work location. Is it in Bangalore or in Mysore? In Mysore? Question mark. If it's in Mysore, what I will do, yes, I will accept the offer. What again I will do, see, again I've come to a pure leaf node, right? A possible outcome. So what I will do, I will accept happily. So I've accepted the offer. Now this is again a pure leaf node. So I don't need any further division, right? So otherwise I will stop here, okay? Otherwise I will reject the offer. What I will do, I will reject. What can you see now? This one, that, and that. These are all my pure nodes, right? My pure leaf nodes. So there is no further division. But the problem arises where, we want to know which one is the root node. Which one should we take as the root node? If salary is my constraint, how about work location? For most people, work location might be the constraint, right? So I need my work location to be my root node. Now, how about, okay, work location is in Bangalore, obviously I will stay there. How about other facilities? Will they be providing bus facility? What are other incentives that the company will be giving? So many of us, especially for the married people, they always consider all this. How will I be far away from my home? My child is so small. My husband needs my attention. My mom needs my attention. My dad needs, all kinds of stuff we have to consider. So you see, knowingly or unknowingly, we make decisions, right? So now the question arises where we have to decide which one becomes the root node. And that's where we have to look into some algorithms, okay? So we look at the algorithms which can enable us to do this stuff, okay? So we know that we have primarily, okay, at this level, we can talk about cats and dog, right? Not cat and dog, okay? CART stands for classification and regression trees, and ID3 stands for iterative dichotomizer version tree. So what you should understand is, apart from CART, we also have other algorithms. So we also have C4.5, where C stands for classification, and we also have C5.0. So these are series of algorithms that are developed by Ross Quinlan, R-O-S-S. So Ross Quinlan, okay. So Ross Quinlan developed these algorithms, okay, that we use to generate a decision tree from a sample data set. Now, when we talk about classification and regression trees, we talk about what we call Gini index. Okay, it all depends on how you pronounce it. Maybe Gini index, I'm not an English scholar. Gini index or Gini index, okay? So Gini index or Gini coefficient or Gini ratio is a statistical measure of distribution which was developed by an Italian statistician, and obviously it was named after him. His name was Colorado Gini. Why I said was because he developed this in 1912, so I'm pretty sure he's no longer alive now. So it was used to gauge the economic inequality of a population. But are we talking about economics here? No. So in data modeling, the same Gini index was extended to measure the inequality amongst values of a variable. So what are we talking about here? We are talking about how whether a variable is homogeneously distributed or heterogeneously distributed. We'll get to this later. When we talk about a pure sample, we know that those samples they contain of the same type. We will see that when we take a sample data set that will decide whether a game should be played or not. Where we have a pure sample of all yes, 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 yes. So the Gini index can be 0 or 1. And we can represent this in form of, since it's a ratio, right? Ratio can also be represented in form of what? Percentages. Please remember it ranges from 0, okay, to 1, where 1 represents an impure data or subsample, okay? And then 0 represents what? The pure subset. I will repeat this again. See, when we have a purely homogeneous subset, and I know you've studied this even in your sciences, homogeneous means it contains the same type. Example, in the data set, if we are talking about a sample that purely has only yes, 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 yes outcomes or true outcomes, then we know that that is a pure sample. So if they are equally distributed, so in statistics we say equiprobable, where we have equal chances of yes and no, equal chances of true and false, we will say that they are what? A purely impure. Okay, I can't say purely impure, okay? They are impure. So, keeping this in mind, we will not look into CAT, okay? Classification and regression trees. We will look into ID tree. Remember, ID tree is just, ID stands for iterative dichotomizer. So what is iteration? Okay, you call it anything, iteration, iteration. So iteration is just about, you see repetition, right? So you've written recursive functions, okay, functions that cause itself iteratively. So you see repetition. So what about that? How about dichotomizer? So here it is a successive division, I beg your pardon. Iteration means what? Repetition. Dichotomizer is division. So it keeps repeating by dividing the entire entire data set into subsets, okay, and calling the functions until we get a desired tree, okay? So, or we get the desired pure subset. So, when we talk about ID tree, we have three primary functions that will enable us to compute that will enable us to get to the desired tree. So the first we look into is the entropy function. So entropy, again, we must have studied in sciences, right? Okay, or it's just an English word, which means what? The rate of disorderliness, or degree, not rate, of disorderliness or randomness. So a pure sample has almost a negligible entropy, whereas an impure sample has a very high degree of entropy. So when we talk about entropy here, we are talking about how pure, okay, how well the sample is represented, right? So that we will compute by using a function. So this is it. It's a very simple thing. If you look at it here, we are saying it is represented as negative what? P positive C minus plus or what? The positive samples, then positive sample of that to base 2, right? Log of the positive sample of that to base 2. Again, minus, see, you have what? Negative samples, number of negative samples, into negative samples to what? Base 2. Now, this maybe you think is little confusing, so we expanded it this way. So you have all the positive samples, say example. So I will give you a small data set and then we will just look into that, okay? So you have this, right? So all the negative samples, fine, divided by the total, right? So if you happen to have a data set that consists of, say, 5 positive examples and 3 negative examples, so why can't we substitute values now? So say the data set has 5 positive examples and 3 negative examples, right? So what will this be now? This becomes 5 upon 8, right? Because see, 5 plus 3, okay? Log, remember, okay? So again, 5 upon 8 to base what? 2, right? Minus, now we are going to talk about the negative examples here, right? So the negative examples here, remember negative is 3, so we say 3 upon, again 8, right? Denominator remains the same. Then again, 3 upon 8 log base 2, right? Now, this is what we are going to compute. So this is explicitly what that formula is telling us. Now, after that is done, we compute the average information entropy. So if you look at it this way, again, it might look like it's confusing. But don't worry, we will take example and then you will get to know this better. So here we are talking about, see this entropy? This entropy is rated as entropy A, whereas this entropy S. So entropy S refers to the entropy of the entire data set. And that of A refers to just what? That particular attribute which we are talking about. So we will expand that later. And please remember, P of I and N of I refers to that attribute, like in the bigger table we have made a smaller subset or a smaller table. So from that smaller table, the P and the N's of I becomes the P and N's of that smaller subset. And then the same P and N is from what? The larger table or the larger data set. Now into the entropy of A. Fine. After that, we calculate the information gain. Please note, we will decide, okay, the decision boundary is drawn based on the information gain. So the one with the highest information gain becomes our root node. But please remember, we cannot just jump directly to the information gain without computing what? The entropy of the entire data set and average information entropy. You can see it here, right? So information gain is expressed as the difference between the entropy of the entire data set and what? The average information entropy. That's why we see that it is what? Entropy of S minus I of attribute. And you can see it here. Okay? So the algorithm looks like this. We compute the entropy for the entire data set, which we call entropy of S. Now, for every attribute or feature, we calculate the what? Entropy for all the values, right? And then we calculate the average information entropy. Then we calculate the information gain for that current attribute. And after this is done, we will now make a smaller table, right? It's usually better if we visualize this in form of a table. So there we compare, we express all the values of the what? Information gain for the respective attributes. So the one that has the highest information gain becomes our root node. So if we get back to this, say I have to decide between whether salary or work location should be my root node, okay? Okay, or work location should be my root node. So there are n number of possibilities here. I have started with salary, and that was my root node. I started with work location. Okay, if I start with work location also, again, I can also check whether to accept or reject the offer. Apart from that, how about incentives? So how about working conditions? See, will I be always transferred, say I'm in Bangalore today, and they tell me, so, no, we have a job in Bombay or Pune, you have to go there. See, you see, the company should tell me most of the things up front, right? So how about the work timings? So should I be working night, okay? Would I be on rotational shift? Or is it kind of a fixed thing where I am sure that 90% of the time I'll be working during the day because I'm more productive in the daytime, right, than at nighttime. So for some people, the work timings might also be a primary factor. So if that is a determining factor, what you have to do again, I also put that also as an option, right? So I'm going to put what? Work timings. So in all these three now, so which one is the best? Okay, where should I start splitting the tree? So because of that, we use the ID tree algorithm, right? So, and then after we have computed the information gain for the current attribute, so we pick the one with the highest gain. Okay, so from there we start splitting the tree. And how long will we do this? We have to repeat this process until we get pure leaves. Now, what happens when we don't get pure leaf, okay? Or what happens when that doesn't converge? Because we can do this n number of times. Remember, it is called iterative dichotomizer. It's successive division. It will keep happening, okay, repeated division n number of times. How long will it go on? If the tree is large, if the data set is large enough, because even you will see here when we take this data set that has about 14 samples, okay, 14 records, and it has about 5 attributes. You see, it takes, for an average student, it takes minimum 30 to 45 minutes to compute the entire subspace. So think about if we have a data set that has about maybe like 1,000 attributes. Okay, sorry, 1,000 records. I'm talking about rows now. Okay, and maybe about 10 attributes. Because in real life, real life data, they're always messy and heterogeneous, right? Consisting of all kinds of stuff, including your missing values also. So in that case, will I do this? Will ID tree work? That's what my question is. So you see, the larger the sample space, okay, or the number of records you have in your data set, the more it takes time. So what happens if you don't arrive at a pure leaf node? What happens now? So you know that there might be some attributes. I don't want to say overfitting now because it's too early, okay? There might be some attributes that are not really necessary, okay? So what do? We need to go back, you know, if you view it like now like a water flow, right? A water flow model, right? So we started from salary and then we moved down until we get here, right? So reaching here, we still know that we did not get pure leaves. So what do? We have to backtrack, right? So that process of backtracking, going back and tracing which attributes really contributed to this or whether they really contributed to this or not, is known as pruning. And that's where SCART comes into play. C-A-R-T, classification and regression trees. So we tried with ID3 and we saw fine, we are not arriving at a proper answer. Then we get back and use what? CAT. Okay? Hope that makes sense. So what we'll do next is we will take a sample data set, right? And then we compute all this, okay? Line by line. And yeah, it's always better if you grab your pen and paper and you follow along. You can always pause the video, okay, and then do that later. But it's always better, you know, when we start, you also start with us, okay? All right.